Hello, my name is Kevin Berg of Charles University, and I'd like to talk to you today about our conference paper, Symmetric Promise Constraint Satisfaction Problems Beyond the Boolean Case. This project was joint work with Libor, Barto, and Diego Battistelli, also of Charles University, and was part of the Symmetry and Computational Complexity project funded by the European Research Council. And the hope with this offline talk is to give you a taste of what most of the proofs in this paper look like and what sort of arguments you can expect if you're to actually go look at the conference paper itself. To begin with, I need to start by introducing the concept of promise CSPs. And to talk about promise CSPs, I have to start by talking about regular constraint satisfaction problems. The constraint satisfaction problem over a finite relational structure A, also called our template, can be defined as a homomorphism problem with a fixed target structure A. Now, analogously, the promise constraint satisfaction problem over a promise template AB, where A and B are both finite relational structures such that A homomorphically maps to B, is a homomorphism problem that generalizes the CSP. The PCSP problem, at least in the search version for template AB, is given a relational structure X such that X maps to A, which is known as the promise, hence the name promise CSP, we want to find a homomorphism from X to B. In particular, please note that the reason PCSP is a generalization of the CSP is because CSP of A is equal to the PCSP of AA. Now, quite a lot of computational problems, such as 3 coloring and 3 SAT, can be expressed in the language of CSPs. 3 coloring is the CSP over the click on 3 vertices, and 3 SAT is the CSP over a binary domain with all ternary relations. Similarly, since PCSP is a generalization of CSP, these problems can also be expressed in the language of PCSP. Furthermore, PCSP is capable of expressing a lot of additional problems, such as the problem of finding an L coloring of a K colorable graph when K is less than or equal to L. This can be described as PCSP on the click of K vertices and to the click of L vertices. Now, CSPs are known to have a hardness dichotomy. Bulatov and Zhuk independently showed in 2017 that all CSPs are either NP complete or they're in P. We don't have a dichotomy like this yet for the PCSP. The strongest classification result that we do have for PCSPs is the dichotomy theorem over Boolean symmetric templates. And when I say a symmetric template, I'm just talking about a template whose relations are all invariant under permutations of coordinates. And this dichotomy for these Boolean symmetric templates has been shown by Breckensiek and Guruswamy in 2018 and Fitzek et al. In 2019. In the computational complexity analysis of PCSPs, there are 2 well-studied cases. There's the case of arbitrary domains with a single binary symmetric relation, and there's the case of Boolean domains with symmetric relations of arbitrary arity. And what we focus on is a case that's in between these 2 well-studied cases. We look at templates where the left-hand side is a single symmetric ternary relation over a 2-element set. And it turns out that after you eliminate known and trivial cases for these types of problems, you were left with problems of the form PCSP 1 and 3b. What do I mean by 1 and 3? Well, I'm talking about a binary domain with the single symmetric ternary relation you see on your screen here. And it's so named because CSP 1 and 3 is the positive 1 and 3 SAT, or corresponds to the positive 1 and 3 SAT. Now, what's interesting about these problems is that they have a natural hypergraph coloring interpretation. So given a 3 uniform hypergraph that is known to be 1 and 3 colorable, PCSP 1 and 3b is saying, okay, I have a hypergraph like this, can I find a B coloring? Now, it turns out that the first non-Boolean domain size, literally B has a domain of size 3, is already interesting for the purposes of coming up with a wide variety of new classifications and requiring new proof techniques and things of this nature. In the conference paper itself, and you're free to go read this, there's a straightforward equivalence that shows that it's actually sufficient to consider the symmetric relational structures with this domain size for all of the classification results we're going to be presenting today. So we're actually only going to be talking about symmetric relational structures with a single ternary relation. And to talk about all of these symmetric relational structures, I'd like to introduce a little bit of shorthand so that I can just throw up some pictures and have those be your reference going forward. Feel free to, pause the video at that slide or go back to that slide if you're so inclined to look at these structures. The shorthand is fairly straightforward. We take a structure B and we associate its digraph to it by taking B as the vertex set, and we include an arc from the element B to the element B prime if and only if the tuple BBB prime is in our relation. The other bit of shorthand we introduce is that whenever we talk about a so-called B plus structure, what we're actually talking about is the basic structure B together with what we call the rainbow tuples, these tuples that are of the form B, B prime, B double prime, where B, B prime, and B double prime are all distinct elements of B. So for example, under this notational shorthand, 1 and 3 becomes an arc between two elements, and NAE, which is the relation corresponding to not all equal, becomes a single edge between two elements. That is to say, an arc from one element to the other and then an arc back again. As I mentioned, these arcs are useful because they allow us to draw diagrams for our three element symmetric structures, and then these diagrams can in turn be modified with the plus notation, which indicates that there's going to be a rainbow tuple. Now, as I mentioned previously, because this is a recorded talk, I'm not going to spend too long on this slide. You can come back and look at it as you see fit. However, I will draw your particular attention to the structure D2. And the reason I'm drawing your attention to D2 here is because the slightly modified structure D2 plus, which is just D2, the symmetric relations together with the rainbow tuples, is going to be the structure that we use for our illustrative examples of how proofs in the paper function later on in this very same talk. So again, if you remember exactly one structure, you should remember D2, and you should remember that D2 plus means D2 together with those rainbow tuples. Now, what's interesting about this broad system of three element symmetric structures is that they can be organized hierarchically based on the admittance of homomorphisms from one structure to another. And I will explain what I mean by that on the next slide here. This diagram that we're looking at now shows the hierarchy of three element symmetric structures. And this hierarchy is established by the existence of homomorphisms. Specifically, if there is a homomorphism from the structure B to the structure B prime, then the structure B prime is higher up in this diagram than the structure B. Why this is of interest to us is that as we move up the diagram, then if a structure has a PCSP from 1 to 3 to that structure that can be shown to be in polynomial time, then everything above that in the diagram also has a PCSP of this form that's in polynomial time. Similarly, if we move down the diagram and we have a structure whose PCSP from 1 to 3 to that structure can be shown to be NP complete, then things below it in the diagram will also be NP complete. Using this, we were able to classify the complexity results of a broad range of PCSPs for these three element symmetric structures. Now, in fact, we were able to classify all but one case of the three element symmetric structures as hardness results. So let's say 1 and 3B is a PCSP template where B has domain size 3. If NAE homomorphically maps to B or T2 homomorphically maps to B, then PCSP 1 and 3B is in polynomial time. Alternatively, if B homomorphically maps to T1 or B homomorphically maps to D1 plus or B homomorphically maps to D2 plus, then PCSP 1 and 3B is NP hard. This leaves the case where B homomorphically maps to T1 plus, which is to say the case where we are considering PCSP 1 and 3 to T1 plus. And so we've left that blue in this diagram of the hierarchy of complexity results for three element symmetric structures, whereas all P time problems are in green and all NP hard problems are in red. Now, to give you an example of the flavor of some of the proofs that are in our conference paper, we're going to zoom in, as previously stated, on the specific case of D2 plus. And in order to zoom in on the specific case of D2 plus and run through the broad outlines of an argument that shows that the PCSP from 1 and 3 to D2 plus is an NP-hard problem, I have to introduce some additional preliminary concepts that cannot be avoided when we are talking about the algebraic arguments that classify the complexity of PCSP problems. The first major concept we need to talk about when we're discussing this algebraic approach is the polymorphism of a PCSP template. And ultimately, the polymorphism of a PCSP template is a homomorphism from a Cartesian power of the first structure in the template to the second structure in the template. To be a little more specific, if we let A and B be a PCSP template, then a mapping from an nth power of the domain of the first relational structure to the domain of the second relational structure is a polymorphism of arity n if it preserves relations. And we have a very specific and careful technical meaning when we say preserves relations. If we have n different tuples that are within the relation in the first structure, then F applied down columns of those tuples will ultimately result in a new tuple that is contained in the corresponding relation in the second structure. So there's a very technical arrangement of vectors in this definition. They are ultimately corresponding to this sort of matrix envisioned mapping. And the reason polymorphisms are so essential is that they are critical building blocks to our analysis of complexity from an algebraic point of view. Most of the work on the complexity for regular constraint satisfaction problems relied on a corresponding notion of polymorphism, and there's nothing different here. And in particular, the NP-Hardness criterion that we are going to be using is completely dependent on our understanding of polymorphisms and our understanding of structures that can only be defined using polymorphisms, in particular, the core concept of a so-called minor. And what a minor is a reduction of a function to an evaluation of that function on a key set of variables. So there's a slightly more technical definition on your screen here, but you can ultimately think of it as, okay, a minor is selecting the key variables of a given function. And the relationship between a minor of a function and the polymorphisms is that the computational complexity of a PCSP depends only on the polymorphisms of the PCSP template, and that set is what we call a minion, and a minion is a set that's closed under taking minors. So all of our polymorphisms determine the computational complexity of our PCSP, and our polymorphisms are ultimately closed under taking minors. Now, in order to discuss our specific NP-Hardness criterion, I need to first introduce one final concept, which is the notion of a chain of minors. And a chain of minors is a sequence consisting of functions together with variable identifications such that each function is a minor under the preceding variable identification of the function that comes before it in the sequence. So there is a very technical definition on the screen, but it can ultimately be thought of as, okay, a chain of minors is a sequence of functions that are related to each other by each being a minor of the preceding function in the chain. So armed with the concept of a polymorphism, minors, and chains of minors, we can talk about the NP-Hardness criterion that we use for several of our NP-Hardness results in the actual paper, as well as the NP-Hardness result that we'll be running through in a few moments as an example proof. And this criteria is due to Brandt, Trochna, and Givney in 2020. And it says that given a PCSP template, if we can find two coordinates such that for every chain of minors consisting of a bounded number of minors of polymorphisms, and each of these polymorphisms has a key set of elements known as the cell set that's of bounded size as well, such that every image of these cell sets intersects with another cell set within the chain of minors, then the PCSP is NP-hard. So it's a slightly technical criterion, and so you can come back to this slide and reference it when we discuss it later on in the proof. The major idea for our purposes is that we identify key properties of polymorphisms based on combinatorial properties, and we use these combinatorial properties to define so-called types of polymorphisms. Then we analyze chains of polymorphisms and argue that certain types have to recur, or if they don't recur, then certain other types have to recur, and then show that these types result in overlapping of these key sets, these sort of so-called smug sets. And now we have enough background information to run through an example proof of NP-hardness results. So this is sort of a typical NP-hardness result for the paper. And if you're interested in more specific ones, I would once again direct you to the actual conference paper wherein we go into more detail for various structures. For our specific purposes here, we're going to be talking about PCSP 1 and 3 to D2+, where D2+ is the structure on 0, 1, 2, consisting of the relations that you see on your screen right here. And to start with, we're going to be considering generic polymorphisms of this template and identifying a few key combinatorial properties that will be used to define those types that we'll use with the criterion. And to discuss these combinatorial properties, I have to introduce a couple of shorthand conventions. So F evaluated at a given set is shorthand for F evaluated with 1 in the ith position for all I in the set, and 0 in all other coordinates. And we say that a set is a J set if F evaluated at that set is equal to J. So to start with, we have a lemma about disjoint subsets of our coordinate set. If, for example, the empty set is the 0 set and one of our disjoint subsets is the 0 set and the other disjoint subset is either a 0 set or a 2 set, then we can actually conclude that the union of those two subsets is either a 0 or a 2 set. Similarly, we can conclude cases where the union is equal to 1, or the union is a 0 or 1 set, or the union is in fact a 2 set. We use this lemma to actually build into some more involved combinatorial lemmata. The details for both the preceding lemma and these combinatorial lemmata are outlined more in the actual paper, but those details are not quite relevant to the overall point we're trying to make here in this short talk. So these combinatorial lemmata break down into specific cases. So for example, if the empty set is a 0 set and our function has no singleton 2 set, then in fact it actually has a singleton 1 set and no 2 disjoint 1 sets. If the empty set is a 1 set and we have certain properties of at most J element subsets being 1 sets, then in fact we can conclude that the immediate next step upsize subset is also a 1 set, which in turn means that there is either a 0 set or a 2 set of size at most 2. And the reason we have all these combinatorial lemmata is that we are going to use them to define our types so that we can apply the NP-hardness criterion. Specifically, we're going to be considering, if you go back and look at the NP-hardness criterion slide, the case where the constant K is equal to 2 and the constant L is equal to 5. We're then going to go ahead and define 3 types of polymorphisms and the critical sets of tuples for those types of polymorphisms. So we say a polymorphism is of type 1 if F has a 2 set of size at most 2. In that case, our set of key coordinates is going to precisely be this 2 set of size at most 2. We say F has type 2 if it has no 2 set of size at most 2. The empty set is a 0 set, and we have a singleton 1 set, in which case we're going to say our key set of coordinates is this singleton 1 set. And finally, we say that a polymorphism is of type 3 if it has no 2 set of size at most 2, the empty set is a 1 set, and we have a 0 set of size at most 2, in which case our key set of coordinates is going to be that 0 set of size at most 2. Now it turns out that by the previous lemmata, we can conclude that every polymorphism of this template is one of these 3 types. Furthermore, it actually turns out via pigeonhole principle that any chain of minors of polymorphisms for this template is going to have two polymorphisms with the same type. And when two polymorphisms with the same type occur, then either those two polymorphisms have key sets of coordinates that overlap, or two other polymorphisms within the chain have key sets of coordinates that overlap. So what this ultimately means is that we will always satisfy the criterion of overlapping sets of key coordinates within the chain of minors when these bounds are imposed. Consequently, we can conclude that the PCSP 1 and 3 to D2 plus is NP-hard. And like I said, this is how a lot of these arguments go for most of the NP-hardness proofs in the actual paper. This then leaves sort of a couple of open questions that now I'd like to draw our attention to, and also directions for further research that we discuss somewhat in the actual conference paper, and that we even prove certain results about, but we do not yet have the full picture for. Our remaining case with a 3-element domain is the PCSP from 1 and 3 to T1 plus. And this remaining case is interesting because it corresponds to a natural hypergraph coloring problem that we believe is new. So given a 1 and 3 colorable 3 uniform hypergraph, we want to find a 3 coloring such that in each hyperedge, if 2 colors are equal, then the third one is quote unquote higher. We conjecture that this PCSP, and indeed its generalization to larger domains, is NP complete. If this conjecture holds, that'll be of interest because there is a unique source of hardness for all of the templates we're talking about. Now, if we're talking about larger domains, such as the 4-element B, our preceding conjecture would actually resolve all the cases with the exception of the interval between two structures we call Che and Che plus. And Che is given by the relation you see on your screen, and Che plus is that together with all the rainbow tuples. Now, we suspect both ends of this interval are NP-hard for reasons I'm about to show you, and we can actually prove that the bottom of this interval is NP-hard. So PCSP 1 and 3 to Che is NP-hard, and the template 1 and 3 Che plus does not have a block symmetric polymorphism with 2 blocks of sizes 23 and 24. This is of interest mostly because this means that it fails the known sufficient condition for tractability in PCSPs, and therefore there are immediate ramifications regardless of which way PCSP 1 and 3 to Che plus turns out. Now, our preceding remarks about T1 plus lead us to talk about the generic K-element domain structure, whose relations are permutation relations BBC, where B is less than C in the standard linear order up to K minus 1. This is sort of linear order K, that structure. LO2 in particular is exactly the structure 1 and 3. And we conjecture that actually for every 2 less than or equal to K less than L, the PCSP of LOK LOL is NP-hard. And as I mentioned, this is a generalization of our earlier conjecture about the PCSP of 1 and 3 T1 plus. Now, going back to that remark we made about Che plus, the remaining cases include the structures in the interval between Che and Che plus. However, we actually conjecture that the PCSP of 1 and 3 to Che plus is NP-hard, and therefore every structure in between those two would also be NP-hard. And the interesting thing about this conjecture is because of that detail I mentioned earlier about the sufficient criterion for tractability in PCSPs not holding in Che plus, if this conjecture turns out to be false, we would also have a very valuable new piece of information because it would require us to devise a polynomial time algorithm that has not yet been used before for PCSPs. So even negative resolution of this conjecture would give us the startling new insight into the greater universe of promise constraint satisfaction problems. And that, as they say, is that. So thank you very much for your time. And we hope you found this a useful introduction to PCSPs, symmetric PCSPs, and indeed the information in our conference paper.